faculty has 8 schools, and just this one school is about half the size in terms of staff numbers, student numbers, and so on. We also are equivalent, or in fact slightly larger than a couple of our smaller faculties. Right? Just this one school is larger than a couple of the faculties. But that aside, I think what really marks us out is the quality of the education and the research that is conducted here in the school. We are very well known, as we know, for the excellent graduates and the technologists that we produce out of the school. I think a number of you are here in the front row as evidence of that. And John had a lot of huge contribution to that in those years. And we are very proud to continue that tradition. So we still we still deliver excellent programs. The programs are kept up to date. We go beyond the minimum that's set in the standard set anywhere else, right? And we do really believe that we are the standard bearers as far as the technological education in this space goes. Research-wise, we are growing. We've got a huge number of academic staff. We are over 70 academics this year, equivalent full-time, and we are still growing. We are currently advertised and in the process of recruiting, and we expect to be around 80 academic staff this time next year. Right, so we are really in the boom phase, and we are keenly aware that we need to maintain standards while the size keeps increasing, but maintain the standards of education, standard of research, and trying to improve even further if that is even possible. In terms of recalling John and his impact on what we do here at CSE, so again, as I said, we have the evidence right here in this room. We are really grateful to the John Lyons Fund Committee, the members of which are here present today. Thank you so much for attending. And we also are grateful to Garnet, who's the John Lyons Chair in the school, and who has done immeasurable work in carrying the standards forward in the operating systems and generally in the systems area of research, both re-establishing research in that area as well as growing it over the years and taking it into lots of new directions. And we will see some exciting talks today, hear them today on the kind of work that's happening more broadly in the area of operating systems as well as in open source, which was also dear to John's heart. Without further ado, I do not want to occupy more time talking about the school itself. So I would now like to hand over and get the stories of John Lyons video to start running. Do you want to hand over to you, John? Garnet? So over to Garnet.
Okay, so now it's time for our first talk by Vanessa Teague, who is founder and main developer, I guess, of a company called Thinking Cybersecurity Pty Ltd, and also has a consulting gig called Democracy Developers. And so that gives you an idea of what she's about, its security, and in particular, how it relates to the functioning of a democratic state, which should be really of core interest to all of us. She's also an adjunct professor at ANU. I first ran personally into Vanessa when a number of years ago, Google ran one of these workshops they do on specific topics. That one was on cybersecurity. And among 50 people or so they invited, they flew us out, etc. Vanessa and I were the only Australians. So that shows you something about her profile in the real world. And in terms of the work she's done over the years, it's a really great example of what I think an awesome academic, and it's a shame that she's not really in academia anymore, because she has done very fundamental work and has taken it all the way to the real world. To me, that's what we as professors should be doing. And so I think she's an example just for that. She did make a number of headlines a few years ago when some government department published a data set for researchers that was anonymized, and Vanessa, the cryptographer, showed that it was not too hard to actually de-anonymize that one. And of course, the government department reacted as you would expect them, by shooting the messenger. That was a really poor show of the democratic system operating, I must say. Not too long later, Vanessa left University of Melbourne and focused on her startup businesses. continuing the general research she's been doing for a while on election integrity, electronic votings, etc. She's done work on verifying end-to-end verifiable election systems. Some of her work was used in the Victorian state elections, but she also did the opposite of discovering vulnerabilities in existing real-world electronic voting systems. In particular, the New South Wales iVote system, which, if you notice, wasn't used in the last state election for apparently good reasons. Also found problems with the ACT internet voting systems and the one used in Switzerland. And Switzerland, in some contrast to Australia, actually trusts their academics, and so they had people from ETH and other top players involved in designing that, and still Vanessa and partners managed to find a man-in-the-middle attack on the certification of the vote integrity, which is quite interesting and resulted in an official thank you letter from the Swiss Federal Chancellor. This is going to be not a deep technical talk, fortunately, because deep crypto is certainly over my head, but I expect a really interesting and entertaining talk. Welcome, Vanessa.
It's about the John Lyons video. There's supposed to be a John Lyons.
Thank you, Gunnar. That was a great introduction. And thank you for having me here at UNSW. It's a real honor to give the John Lyons talk because it makes me feel like I'm part of a actually really good, really long-standing tradition of Australian computer science. We sometimes feel like we're a bit of a backwater here, but actually we've been doing good stuff in this country for a long time. So the theme of my talk is using computers in elections without throwing away the secret ballot and the integrity of the process. And I really want to get everybody thinking about what election verification and election scrutineering should look like in the modern world. So here we go. I should say, many of the ideas in this talk are joint work with a very large number of people. The specific technical ideas are joint work with Michelle Blom, Andrew Conway, and Peter Stuckey, primarily. So, Australian elections are very boring. Why do other countries' elections look like this when our elections look like this? This is my local with a group of people standing in a queue, behaving in a very civilised way. I was frightened in our last federal election that we would have violence that looked like this, but actually we had absolutely nothing of the kind, not even close. And even this situation is actually worse than you think if you wander around America now. Not only was there a small number of people who engaged in violence, there's a large number of people who don't believe the outcome of the election, which is a catastrophe. We basically don't have that here. So it's worth asking, why do some countries have that problem and other countries not? I'm interested in voting technology. So although I acknowledge that there are a zillion other differences between the countries that have serious problems and countries like us that so far do not, I do see substantial differences in the voting technology that has been used in the different places. Brazil and the United States have both had substantial dependence for a long time on basically completely unverifiable voting machines. There's kinds of, on the left is an American one, on the right is a Brazilian one, and they both have this concept that you walk up to the machine, you press some buttons, and then you kind of walk away and hope for the best. We don't have this in Australia, except in the Australian Capital Territory, and even then only for ACT elections. So that's very bad. And I think that forms a foundation of actually quite well-justified distrust that fuels a lot of violence. However, it has to be said, most of the paperless electronic machines were gone by 2020. So there's obviously more to the story than that. Conversely, Australia has almost all manually counted paper ballots, which are a very good evidence trail that can be easily scrutinised. On the other hand, you all know iVote went down and messed up the local government elections and there were no riots, even though there had clearly been a substantial technical failure. So I don't want to oversimplify and act as if it's only technology that makes a difference, but I'm going to talk about the technological differences because I think they do have an influence, even though they're obviously not the whole story. Okay, so let's distinguish three different kinds of attacks. So one is actual physical violence, which fortunately for me is outside of my understanding. There's a kind of what I would describe as a psychological attack on an election, where people try to persuade the mob that the election has been stolen, even though they don't have any evidence of that fact. And then the last thing to think about is, I guess, what a computer scientist would think about, which is actual technical breaking into the computer or taking control of the computer and fiddling with the election results. And I guess the theme of my talk is to say, genuinely generating evidence of an accurate election result is a way of defending against both the technical attacks and the psychological attacks. If we design our electoral systems so that fiddling is evident and evident to the public, then we defend ourselves not only against successful technical attacks, but against the kind of psychological attack where people try to pretend that something's gone wrong even though they don't have any evidence that it has. Okay, so let's talk a little bit about how Australia came to be this way and why Australian elections are famously boring. If you haven't read this book, I highly recommend it. It's called From Secret Ballot to Democracy Sausage by a Victorian academic called Judith Brett, and most of the quotes for the next few slides are from her. Starting with this one. Okay. In 1843, elections were held for 24 members of the 36-member Legislative Council of New South Wales. For the election, the colony was divided into 24 districts, of which Port Phillip, now Victoria, was one. In other words, Victoria was not separate from New South Wales at that time. The first elections were run according to the British practice. Here's a little newspaper clipping that I found online from about 90 years later. It says, "Excitement ran high on polling day. As each elector handed in his voting paper, the returning officer called out to the crowd at the booth for whom he had voted." So right, imagine like you walk up with your vote and there's a guy sitting at the desk and he reads out your vote aloud to everybody else at the pub. Applause, hisses and threats greeted the voter from the rival factions. We cannot wonder that 235 of the 791 electors on the borough roll refrained from voting. So voting was a bit of an ordeal. Okay, so when did it change? Well, conclusion. So this is Judith Brett again. In 4 districts, including Sydney and Melbourne, Australia's first election day ended in violence and riots. Police and soldiers struggled to control drunken mobs armed with staves and pickets. So we didn't always have nice, peaceful, civilised, calm elections. Not at all. We had to do something to change this state into the calm, peaceful state we now all take for granted. And that something was a technological change. It was invented for the 1856 Victorian election, which was the first election in which Victoria was split off as a separate colony from New South Wales. And the technology was specifically and deliberately designed. So Nicholson moved that elections be conducted by the secret ballot. He argued that it would prevent the practice of treating because nobody would bother trying to bribe a voter if they couldn't tell whether their bribe had paid off. And they designed a system that is pretty much exactly what we use today, that the voter picks up a ballot from the polling clerk, marks their name off the roll, and then goes into a private place to vote, and then comes back, puts their ballot into the public box, and then they get counted publicly later. So the main interesting thing that I want to say about this is they could have solved the privacy problem by just hiding everything behind closed doors. But they didn't. They did something much more clever. They solved the privacy problem without sacrificing the public evidence trail. So they still had the public ballot box in a publicly visible place, and they still had public counting. The only difference was that now the actual vote from each person was expressed in private, even though you could still see the person putting one vote into the box. Some people call this the invention of the secret ballot. It's not really fair to say so. A lot of European countries were using systems that achieved more or less the same objective already, but it's the invention of the thing that we now use, and which has subsequently spread across a lot of the English-speaking world, even including America and New South Wales. It's not a new idea, it's an old idea. The Greeks used to do the same thing with bronze discs, which they would drop into an urn and then count later. So you could see each voter, actually each juror in this case, drop their bronze disc into the urn, but you couldn't see exactly what kind of disc they had dropped, and then they counted them all later. So there's nothing special about paper, but there is something special about this security goal of making sure every individual person's contribution is private, while also providing a public evidence trail that everybody can watch. We do a pretty good job in Australia, and we have for a long time now. This is a photo from the 90s from the AEC website, in which you can see the two people at the front are election officials. They're actually counting the ballots, and the people standing around behind are candidate-appointed scrutineers who are allowed to watch the process. And that process works great, particularly in the old days when almost all electorates were one or the other major party. They would literally just sort the pieces of paper according to which of the major parties was higher up, and that gave the scrutineers a very good idea of who had really won. So that was great, but it's increasingly not useful because, for one thing, a lot of people vote early. For another thing, a lot of electorates have more than two serious contenders. We have independents and Greens, and our elections are getting a lot more complicated. For another thing, there are just more people voting, and the manual counting process is becoming hard to do. So sooner or later, this is going to go electronic, I suspect. And in fact, there are already proposals in Victoria to do this process via electronic scanning rather than by hand. The Senate has been counted this way for a long time. There hasn't been manual counting in the Senate since the 80s. People type AEC officials type what they see on a Senate ballot paper into a computer screen. And the scrutineer's role is restricted to standing around watching people type stuff into a computer. If you ask the AEC about this process, they'll say, it's just as good for scrutineering as this other picture, right? The scrutineers are still allowed to stand there. They get just as much evidence that the right thing is happening because they can see that the person is typing the right thing into the computer. I think that model is totally wrong because you can't really tell what the computer is doing. So the fact that the scrutineers are able to stand around in the room doesn't really give those people any evidence that the pieces of paper are being accurately digitised and properly counted. So a very large part of my research over the last few years has been trying to think about this situation where we have an evidence trail. We have some third parties who are interested in verifying this evidence trail, but we're using computers in a crucial part of the process, and we can't necessarily tell exactly what the computers are doing. Okay, so here's the idea. Here's the setting. The setting is people vote on paper. They submit their piece of paper into some anonymising physical box. But then we digitise those pieces of paper and count them electronically. And the question is, how can we verify that the electronic scanning and counting process has been done right? So there's an American solution that has been in place for a long time, long before I started looking at this, in fact. It's called risk limiting audits, and it was introduced by Philip Stark and a small number of his students and other co-authors, but mostly Philip Stark's idea. So the idea is you start with a paper trail, that you trust, because there's no point auditing a paper trail that you don't trust. And you start with some kind of set of electronic records that are supposed to accurately reflect the paper ballots. But you start with skepticism because you don't necessarily believe that the electronic process has accurately captured what's on the ballot papers. And the idea is to use statistical methods for randomly sampling the ballot papers, looking at how many discrepancies you have and trying to make a confident assessment, either that the number of discrepancies is low enough that you can be happy to endorse the apparent election result, or that the number of errors is so high that you need to go and manually examine the ballot papers again. So the only problem with this setup is that Americans all use a primitive form of voting called plurality, in which all you get to do is choose your favourite candidate, and then they just tally them up, right? So there's wonderful open source implementations, there's all kinds of good stuff, but it doesn't work for for the preferential voting style that we use in Australia. Okay, but just to summarise what the security goal is here, it's the following. We want to be able to choose a risk limit in advance. Think of maybe 2% or 5%, depending on what level of risk you're willing to accept. We want to choose that in advance. Sometimes it's written into legislation, and we want to say, let's say 2%. We want to choose our auditing process so that we can be confident that if the election result is actually wrong, if there's been a malfunction in the scanner or whatever, then we won't accept that wrong result except with 2% probability. So this is a parameter that you set in advance, and that's really the critical security property of this whole method of doing this thing. So here's a little picture to give you an idea. So think about just an American-style plurality election with 3 candidates. One of them gets 40%, one of them gets 31%, and one of them gets 29%. Then what we're doing when we randomly sample our ballot papers and check for discrepancies is we're just asking the question, can we be confident that the error rate is less than 9%? Because that's what the apparent discrepancy is, and if we haven't got an error rate bigger than that, then we're safe, and we've got the right answer. At the time that we started looking at this, there was quite a lot of interesting literature about how to do the statistics. I think we'll just skip that slide. And all kinds of clever refinements, right? For example, you don't necessarily need to panic about every different kind of error. If you get an error that seems to have understated how much Alice won by, then actually you don't even need to count that really, because that doesn't contribute towards flipping the result. You really only need to worry about errors that overstate the person who appeared to win. So another way that we could ask the question and get more confident more early is to say, is the overstatement more or less than 9%? So there's a whole lot of papers with a whole lot of more sophisticated statistics about doing a better and better job of more efficiently assessing whether or not your plurality election has been accurately counted. Here's a little picture of the audit flow. There's actually quite a lot that goes into it. You have to get the electoral authority to commit in advance to what their interpretation of each of the different ballot papers is. You have to have a transparent process for randomly selecting those ballot papers, and you have to give observers the opportunity to participate in the seeding of the random number generator. But the crucial thing that you get out of it, assuming that all of these components are open source, is you really get a genuine public evidence trail, because anybody who's observing the audit and looking at the piece of paper can be replicating all of these computations and checking for themselves whether or not the audit has been properly done. Even if they can't check whether the initial count has been properly done, they can be redoing all the steps of the audit. In practice, most of the implementations that I actually know about fall a little bit short of giving election scrutineers complete opportunity to get all the data they need to completely replicate the calculations, but at least in principle, this way of doing things has the potential to, at least in principle, this way of doing things can be replicated by observers. Okay. But that doesn't do Australia any good, because so far we've only been talking about first past the post. So if your ballot paper doesn't look like, choose one, if instead your ballot paper looks like this, then at the time that Michelle Blom and Peter Stuckey and I started looking at this problem, there was no solution. So there were no known algorithms for doing risk-limiting audits that worked efficiently for Australia's electoral system. Who's voted in an Australian election? Fair number of people. Who's never voted in an Australian election? Enough people that I will explain how our complicated counting system works. Okay, so your ballot looks like this. You don't just choose your favourite candidate, you list them in preference order. So this person has participated in the ancient Australian tradition of donkey voting and listed the first candidate as their first preference, the second candidate as their second preference, and so on. Tallying goes like this. And it's easiest to think of if you just think of it as being literally done on a table, like the picture I showed a little while ago. The first step is they pile the ballots according to who's the first preference. And then they look and they see whether anybody has an absolute majority, that is more than 50%. If nobody does, they take the candidate with the smallest pile, they pick up all those votes, eliminate that candidate from consideration, and then for each ballot on that pile, they look at the next candidate who hasn't been eliminated yet and they put the piece of paper on that person's pile. And this process keeps going until somebody has more than 50%, and then we're done. So now it's not at all obvious, if this was done electronically, it's not at all obvious how you do the statistics for assessing whether or not it had been done properly. So think for a minute about what happens if we want to, suppose we've just got three candidates again, Alice, Bob and Chuan, and suppose Alice's first preferences are 40%, Bob's first preferences are 31% and Chuan's are 29%. One obvious thing that we could do is we could just do an audit for every single one of the elimination steps and check specifically that each elimination step had been done correctly. And that would be sound, but it could also be a total waste of time, because it might be that it actually really doesn't matter whether Bob or Chuan get eliminated first. It might be that actually they've both given Alice their second preferences anyway, so we don't need to waste a whole lot of time checking that particular elimination. So this method is correct, but potentially very, very inefficient. So then our second idea is first analyse all the votes. Like, get the digital preferences, look at them really carefully, calculate what the margin is. And then after you've calculated what the margin is, in this example it might be 2% or it might be 9%, depending on how the preferences flow. After you've done that calculation, then do your audit to detect how many errors there are. And if there are fewer errors, if you can be confident that there are fewer errors than the real margin, then you're done. This, again, is sound and is a fair bit more efficient than the thing we mentioned a little while on the previous slide. But it's still not great, and it can still waste a fair bit of time because it counts all of the errors as if they were equally bad. When in fact, if you've just got a bunch of random errors, it's much more likely that they all just cancel out. So this again is sound, but we can do better. So here's the clever idea, which again is joint work with Michelle Blom and Peter Stuckey. We started looking at this. So Michelle and Peter are constraint optimization specialists. And they started looking at this and said, well, let's try to look at how we could design an audit that is as efficient as we can make it. And what we're going to do is hunt for things that we can check that have a relatively large margin, because it's relative. You don't need very many samples to confirm something that has a relatively large margin. So we're going to run an analysis on the preferential votes before we even start auditing. And the analysis is going to generate for us a collection of assertions about the election. And they're going to say things like, when only Ellis and Bob are still standing, Ellis has more votes than Bob. Or when only Chuan and Diego are still standing, Diego beats Chuan. And the algorithm's objective is well, first of all, its correctness condition is the set of these assertions has to imply that the announced winner won. And then the kind of heuristic that we're trying to achieve is they're supposed to be relatively easy to check, to verify by our risk limiting audit. The easiest way to explain it is to imagine the complete set of all possible IRV outcomes. So imagine everything that could possibly happen in an IRV election with 4 candidates, creatively called A, B, C, and D. Right? This tree represents all of the outcomes that end with Alice winning. And each elimination sequence is a branch of the tree that goes all the way down to the leaf. So for example, this one on the right with B at the leaf represents the elimination sequence where Bob gets eliminated first, then Chuan gets eliminated, then Diego and Alice are left, and Diego has fewer votes than Alice. So we can arrange all possible election outcomes in trees like this, and our job is to make up assertions that exclude the possibility of anybody except the announced winner winning. And then we're going to test whether those assertions are true using a risk limiting audit. So, I think I said this already. The idea, if you like to think as a computer scientist, is to reduce the IRV outcome to a series of 2-candidate comparisons that are just like the ordinary plurality comparisons that the risk limiting audit is already designed to do. Okay, so we made up 2 kinds of assertions. One of which I think is, so the one at the top is very familiar. Basically, that it says, when I've got a certain set of candidates who are still standing, I'm going to test that a certain person doesn't get eliminated next. The other is much more general and really allows us to rule out the huge number of little candidates that really haven't got a chance of winning. And we call it never eliminated before. And the idea is I can say W is never eliminated before L if W's first preferences are so numerous that they're greater than the total number of times that L even gets mentioned without being preceded by W. And if you think about how IRV elimination works, this means that there's no situation, regardless of who is eliminated or what happens in the order of the tallying, in which W can ever be eliminated before L. So W is always going to have a higher tally. So the idea is to string together a collection of assertions of this kind that together imply that the announced winner won, and then to test each one of our assertions with a risk limiting audit. So here's a picture for just as an example. Suppose we were told that Alice won the election. Then we've got to get rid of every single path in the trees where Bob and Chuan win. If we have an assertion that says Alice is never eliminated before Chuan, then we can immediately get rid of the whole tree at the bottom. There's no chance that Chuan can win if Alice is never eliminated before him. We could also get rid of some of the paths on the tree in which Bob wins. That's depicted up the top. So we can get rid of some of the paths where Alice is eliminated before Chuan, but we're still left with some other paths by which Bob can win, and we're going to need another assertion to get rid of them. This is a sufficient set of assertions, which you can check later if you want. We don't need to worry about getting rid of the case where Alice wins, but we can add a few more assertions of various kinds to get rid of the case of everything other than when Alice wins. And then we can put these assertions into a risk-limiting audit engine and use that to verify whether the announced winner won. To put it another way, if we've been told a lie, if our scanning system has malfunctioned and Alice didn't really win, then one of these assertions must be wrong. And when we test it with a risk-limiting audit, then the RLA guarantee should say that, except with the small probability that we set in advance, the audit should refuse to accept that assertion. And when that happens, we're going to refuse to accept the election result. Okay, actually generating the assertions is hard, which is why we needed a constraint optimization specialist team in Michelle Blum and Peter Stuckey. But all of the code for doing so is openly available on GitHub, as you can see. Furthermore, you don't have to trust the assertion generation code. All you have to do is examine its outputs and verify that that set of assertions is sufficient to prove that the announced winner won. And there's a couple more pieces of open source code that you can use if you like, or you can write your own to check whether a certain set of assertions really does imply that a particular person won. Okay, so we piloted this in San Francisco in November of 2019. It wasn't a real election audit because we only looked at the vote by mail ballots. But apart from the fact that we were only looking at a little subset of the election, it was otherwise, we went through the whole process of auditing the outcome. Here's a picture, again, somewhat analogous to that picture I showed a while back of Australian scrutineers watching people shuffle paper around. The people towards the front of the computers are election officials actually doing the work. The people standing behind are just citizens who felt like showing up and watching the electoral process. I don't know whether any of these people actually took the opportunity to double check the calculations with the open source code, but they could have if they wanted, and they had all of the information available to them, both in terms of seeing the paper ballots that were being sampled and in terms of having the code that they could run themselves if they wanted to double check the calculations. There we go. We sampled 200 ballots. We generated 11 IRV assertions. It was a very small election with only 4 candidates, and attained an overall risk of 3% because there actually were almost no errors. 10 minutes, thank you. So that was good. This process is going to be used in Colorado in 2025, where they already have an open source risk limiting audit system for their plurality elections, and they're getting us to expand it to instant runoff voting because they're introducing instant runoff voting for some of their local council races. It could be used in Australia, although it never has been. At the moment, we don't have risk limiting audits in place, which is fine as long as we're manually counting. But as we switch over, if we switch over to electronic counting, we will need to introduce something like this. Okay, so far I've talked about the single winner case, which is relatively tractable. The next thing to consider in the last 10 minutes is the proportional case. So I haven't got a slide explaining how STV works because it doesn't really fit on one slide, but it's basically the proportional version of the instant runoff algorithm that I showed a few slides ago. So we not only go through a process of eliminating people who have a low tally, we also at each step set a certain quota for getting a seat. So for example, if there's a if there are 5 seats going, which there are, for example, in Victorian upper house elections, then anybody who gets a little over a sixth of a seat, of a fraction of the vote, can get a seat. And so there's quite a complicated algorithm for simultaneously redistributing the preferences of the people who got a seat and also eliminating people who have a very low tally when nobody got a seat. This is a lot more complicated than the single seat instant runoff case, and we do not have a good solution for auditing this at this time. But something has to happen, because this is actually the thing that does get counted electronically. So this picture is from the Australian National Audit Office's simplified diagram of the Australian Electoral Commission's Senate scanning and counting process. On the far left-hand side of a very big complicated diagram, paper ballots come in. On the far right side of the big complicated diagram, digitised preferences come out, and they are posted on the internet. So the AEC actually does that well. So you can go and download the complete set of preferences for the last Senate election and recount them yourself. We don't have to worry too much about the counting step. What we have to worry about is this great big complicated purple process in the middle. So how do we know whether or not the paper ballots are accurately transcribed into the digital preferences that get posted on the web? I asked for years and years and years and years and years what the error rate was. And I didn't get much of an answer until in 2021, with multi-partisan support, the Federal Parliament passed the Electoral Legislation Amendment Assurance of Senate Counting Bill, which is sort of, they threw into it everything that could possibly make anybody happy. And one of the things that they threw into it was this, which made me happy, which was a requirement that the Electoral Commission must take a random sample of paper ballots and audit them against the digital preferences in order to assess the error rate. This is just the best thing that has happened in federal government legislation in 20 years, in my opinion. Because it really is a huge step forward, both for the real and the perceived security of the Senate ballot digitisation process. Okay, so they sampled 10,000 ballots, which is a lot, and it sounds good, except they didn't sample them randomly, they just took the first one from each colour that they organised. But anyway, better than nothing. In 33 cases, when they compared the ballot paper with the digitised preferences, they realised that the marks were incorrectly interpreted, and that's expected, in fact that's relatively low. In 6 cases, they couldn't find any matching digital image in the database, which is not really expected. But I guess it's better to know than not to know. So could we do better? And I think the answer is we could do a bit better. Not quite as well as we can do for IRV, but better than the very ad hoc methods that were used in our last Senate election. We have some heuristics for assessing the margin, which are not perfect. It's more of a search algorithm. So we can get a bound on the margin, even though there might be another smaller manipulation that we can't find. We could use that bound together with a rigorous assessment of the error rate to just see whether the apparent rate of errors was less than the margin. And if it was, we could be confident we got the right result, and if it wasn't, we could investigate further in some way. And that would give us a somewhat more rigorous basis than the existing process, although it wouldn't give us the risk limiting guarantee that we know how to do for the single seat case. Okay, I'm almost done. Future work on this, I'm almost done with this section rather. Future work on this work is getting the risk limiting audit property for STV, which we currently don't know how to do because it's too complicated, but we do know how to do for some special cases. Really making good quality software to actually do the audits. At the moment we have this nice kind of open source, you can re-implement it yourself kind of vibe, but nobody's really looked at pinning down precisely how to prove that that protocol provides public verifiability. And then the third is obviously attempting to explain it to the public, for which we have started but not finished. So the interesting research problems are all about extending this notion of public evidence to more scenarios without sacrificing the secret ballot. I've got 3 minutes left. Is that right, Gunnar? All right, I'm going to spend my last 3 minutes. I can't come to New South Wales and give a talk about election security without at least mentioning iVote. So if you're sitting in your seat thinking, but wait, wouldn't it be better if we could all vote over the internet? And wouldn't that make our elections just as secure as everything else on the internet? The answer is yes. Yes, it would. You could, but you shouldn't. It's not the reliability issues. It's not even that it's much easier to fiddle than other methods of voting. It really is that we really don't know how to provide a public evidence trail over the internet without sacrificing the secret ballot. So there are various kinds of fancy cryptographic mechanisms, including end-to-end verifiability, none of which have ever been tried in New South Wales. And they are real, but they still have this serious problem that really giving a person evidence that their electronic ballot has been accurately recorded is just really hard. And we don't have a usable solution that is secure and that actually allows ordinary people to do it properly. I think the New South Wales Electoral Commission says it best for themselves. This is from their most recent, as far as I know, their most recent publication about iVote. So TAV is technology assisted voting, for which you can read internet voting. This is their interim review report, paper 2. It's clear they were embarrassed about the whole Supreme Court thing. And what they've suggested is we can solve the problem of internet voting failures leading to election reruns by excluding internet voting failures from the kinds of things that you're allowed to argue about in the Supreme Court. So read the fine print very carefully. It says, it appears appropriate and proportionate given modelling based on previous results data and the proposed small scale of technically assisted voting for an election not to be invalid on the basis only the technically assisted voting was not available. And in fact, it gets better. They're not just solving the last war, they're thinking ahead now. It also may be appropriate to extend such protection to address risks of performance issues after votes have been cast. So we're not just thinking about not being able to ask the Supreme Court to void the election because the system went down. We're also thinking about if the database goes belly up a week after the election and they can't count the iVotes, you're still not allowed to take them to court. And really, I can't think of any more eloquent way of arguing that this is a rotten way to run elections. All right, now I really am done. Questions are welcome.
Okay, thank you very much. So the Slido link is up there for questions. You're also welcome to ask questions just by raising your hand, and I run around with a microphone. And my colleague, Carol?
Hi, Vanessa. The way in which the voting is carried out is defined by legislation, I guess, an act of parliament or something, as its defining moment?
Yes.
Yeah. So when you're analyzing the mathematical view, which you've explained here, what legal standing does the view you have taken have? How do you show that it's the same as what's written in the constitution of the state or the country?
I'm sure my interpretation has no legal standing, Carol. I'm not sure what the...
Well, in that
I'm
case,
not sure I understand your question.
When you come to the conclusion that a certain proportion of votes is sufficient to make sure that nothing went wrong, you're referring to your understanding,
That's
your
right.
mathematical understanding, but that is not actually referring to the
That's right. There is no risk limiting order legislation.
So that's not
anywhere
intended as
in
a
Australia.
criticism.
There is in Colorado and California,
Yeah.
but there is none in Australia.
So it's not intended as a criticism, but more looking ahead to see whether that's a problem that's downstream for you. Actually legitimizing at that level what you have decided is the model of the voting system.
Yes, absolutely. So I think what you're saying is there's no hope persuading the electoral commissions to do this kind of auditing when they're not required to do so by legislation. Yes, absolutely, that is true. And in fact, the Federal Electoral Commissioner 2 cycles ago was asked by Senate estimates whether he would conduct an audit of this kind, and he literally said, I will not do so unless required by legislation. And so then they wrote the legislation that required him to do so. But none of the other states have yet followed suit. And that federal legislation that I mentioned, it's a lot better than nothing, but it's definitely not what I would have written. So it doesn't require random sampling, for example. It doesn't require a level of sort of public disclosure that really allows for third parties to check that they've done the right thing, and so on. So it's not. It's a step forward, but it's not a perfect piece of legislation by any stretch. Interesting. I have no idea. Right? I have no idea what would happen if you started arguing about it. Yeah.
Two questions. One for the entry of the data. There was still a single computer, and nobody's going to remember what were all the things that were entered. So it would be better to have a distributed process with sort of a call out. Each party can type in for themselves and then run a consensus protocol afterwards.
That would be another way of doing it, right? I mean, so that way of doing it is an interesting, different thing from what I was suggesting, right? What you're saying is that the initial process could be more distributed among a wider number of people in the first place. So one person enters the ballot, one person from the Labor Party enters the ballot, and then they pass it to someone from the Liberal Party who enters to the ballot, and they pass it to somebody from the Greens, and then they all make sure that they agree. It's an interesting, I hadn't really thought about that way of doing it. At the moment, at least the tradition in Australia tends to be that the electoral commissions do the process and the scrutineers kind of only get to watch. What you're saying is interesting, but it would mean that the observers would have to be very actively involved throughout. I don't know, it's an interesting idea though.
Second question is a technical one. When I see your trees, and I think of like New South Wales Senate papers, which have the order of 100 candidates, what's the number of assertions that you actually need?
Very large.
As a complexity question.
So, yes. So we haven't looked seriously at trying to generate the assertions for the New South Wales Legislative Council or the Senate because they're too huge, right? But for the single winner case, we can get if there's only 4 candidates, you end up with a very small number of assertions, like 11, for example, for San Francisco. But it grows quickly as the number of candidates gets larger. And by the time you're looking at, 10 or 14 candidates, you can have hundreds of assertions, which is fine because only the computer needs to do 100 different calculations. The people only need to go and fish out one ballot paper and then deal with it. Yeah. Right. So in principle, if you had 100 assertions with the same very close margin, you could actually end up doing a lot more auditing than if you were only doing one comparison with that margin. And you can definitely, if you really want to be nasty, you can set up preferential elections that have a whole lot of close pinch points like that. In practice, real voting patterns tend not to have that. There tends to be really only one particular decision point where the margin is close, if that, and then the other things tend to have larger margins. So in principle, what you're saying is definitely true. It could take a lot longer to audit than a plurality election with an equivalent margin because you're effectively auditing maybe hundreds of things at once. In practice, it usually doesn't, because you usually don't get lots of things with a small margin.
Okay, question from Slido, which I'm personally interested in as well, I must say. Estonia has had a full electronic voting system and it has been used for years. How did they overcome the integrity and security concerns?
They didn't. They didn't, right? So Estonia, there are some pieces of infrastructure they have that's better than Australia. So the main piece of infrastructure they have that's better than Australia is digital signature, a universal public key infrastructure for citizens, right? So citizens sign their vote before they upload it, and that makes a certain class of attacks a lot harder. It's a lot harder to just, steal someone's electoral roll data off the internet and pretend to be them and vote on their behalf. So that's part of the solution, but the solution is really not complete. There are bugs in the Estonian electronic voting system, and my colleague Olivier Pereira actually found one quite recently relating to, they have this, what they characterise as a coercion resistance feature, which is that you can re-vote. So you vote once, if you've been coerced or you change your mind, you can vote again, which is fine. I'm not convinced that it's an adequate defence against coercion, but anyway. Olivier showed that if your voting computer is malicious, it can re-vote on your behalf, even though you've carefully verified the first vote that you cast. So the re-voting feature, which is supposedly the defence against coercion, actually breaks the verification that you cast the vote that you wanted.
Okay, and a related one, what went wrong with the Swiss system?
Oh, what went wrong with the Swiss system? So they had, I need slides actually, what went wrong with the Swiss system is a cryptographic issue. They had quite a sophisticated protocol for mixing electronic votes. So the idea was there was a set of vote ciphertexts that came in. There was a series of mixing servers that re-randomised and shuffled the votes, so sort of an electronic equivalent of putting them in a ballot box and shaking them around. And this is critically important for privacy, right? Because on the input side, whose ciphertext is whose. So we really need to shuffle them in order to safely decrypt them without breaking the secret ballot. But it's also clear that the computer that is doing the shuffling has the potential to fiddle the votes, because they take a bunch of ciphertexts in one side and they output a different set of ciphertexts out the other side. So there's in fact a whole literature about fancy cryptographic proofs that when you've shuffled a set of ciphertexts, you didn't change the set of plaintexts. And the short answer is the Swiss implementation of the proof that they were using was broken, and it was actually possible to generate a proof that passed their verification algorithm, but actually repeated some of the votes and dropped some of the others.
Thank you so much. You started your talk with motivations surrounding public trust and the lack of it. And the sort of elephant in the room was that if people don't understand the voting mechanisms, then it's pretty easy for narratives to the contrary of public stability to get a foothold and things to go awry. And the example you gave in Australia was one where just about anybody can understand the nature of the checking of the electoral results, and thus trust is not undermined. But when you're talking about the technology assisted voting, the way that electoral observers would check this voting involved downloading the source code, running something on their computer. So I'm wondering, how many people in Australia do you think generally understand how to do this? For that matter, how many people in Australia even understand that sentence? And to what extent do you think that the answer to those questions might undermine the very trust in the electoral processes that motivated your talk? So thank you.
It's a really good question. And I would say it's actually even a little bit worse than you think, because there's a significant effort to provide what looks like evidence that is actually not sound. So it's not just can people provide can people understand genuine evidence when it is provided? It's also can people reliably distinguish real evidence from nonsense. And unfortunately, I agree with the assumption behind your question, which is the number of people who can reliably do that, let alone communicate it in an effective way to the public, is almost zero. This is the best I can do, but I would not in any way claim that it is sufficient.
Okay, one more question from Slido. During census, some countries must count all citizens, not just samples, and extrapolate. Here, votes are counted. Verification is by sampling. Comments.
Say it again slowly. I'm not sure I understand the question.
So, in Australia, rather than counting all the votes in the census, it's just sampled apparently, and I think other countries just do statistical sampling of census. So, question.
I can explain.
Oh yeah.
Basically, in India, for example, population is counted by sampling, so they don't attempt to count every single head, out there, male, female, child, whatever. So it's sampling, and then they do a bit of extrapolation based on that and announce the numbers. Whereas here, I'm told that by legislation, you have to actually count everybody physically. You're not allowed to sample.
In the
Certainly
census.
In the US. Yeah.
Yeah.
So I'm asking, in comparison to that, here the voting is individual. Everybody individually votes electronically or whatever. But you're saying that you'll provide verification by sampling. You're going to sample some of the votes and then do some reasoning over that, and then conclude whether within an error margin, whether it's been appropriately counted or not. So any comments on that? I mean, the use of sampling in this context.
Well, it relates a little bit to the question from further back in the room, which is, it's all very well to say you did some clever statistics and you sampled randomly and this is your inference, but what if people don't accept that? And I think the answer is if people don't accept that, then you have to go back to manual counting. Right? There's a lot of controversy over the manual count that was done in Georgia, for example. When tensions were running very high, there was a decision made to count manually. There's one school of thought that says a statistical audit would have been just as good and would have taken a lot less time. There's another school of thought that says it was much better, given the level of tension, to do a full manual count because that was more convincing to everybody, including people who wouldn't have wanted to understand the statistics. So I think both perspectives are valid, right? And I don't really have an opinion about how easy it is to convince people to accept scientifically valid evidence, particularly if there are people working hard to persuade them that it's not true. To do it here, yes. Yeah.
Okay, I think we'll leave it here for questions. Vanessa will be around in the break, of course. And obviously I couldn't do this job without stuffing up, and I have. So the stuff up was that I forgot about the 2-minute John Lyons video, which was meant to be played before Vanessa's talk. First, let's thank Vanessa, and hopefully they'll bring up the video.
Well, I was doing a PhD here in the department between 71 and 75, and John turned up, I think, in 1970.
Okay, so our second talk for today is by Timothy, or short Timothy Roscoe, who is professor at ETH Zurich. Timothy is someone who I have known for many years, and he's been building operating systems for many years. He's one of the few people around the world who are still actually building operating systems. That's a skill set that's sort of getting lost. It seems to be more interesting to write language models that give you wrong answers than to write operating systems that make sure you get the right things. So, Timothy did his PhD in the mid-90s at Cambridge, working on the Nemesis single address space operating systems, which was sort of an interesting coincidence because we were working on single address space operating systems at the same time. He then spent some time with a startup in the US, joined Sprint Labs, and then later Intel Berkeley Labs. And between that and taking up his new job as a professor at ETH Zurich, he spent actually some time with us here at UNSW and then NICTA. And then he went on to create or pioneer an operating system design that is called a multi-kernel. So this is a microkernel-based operating system design that really scales to a large number of processors by getting away from the limitations that you get from sharing kernel data structures. So he created this barrelfish operating system that was published in 2009, for which he was admitted to the ACM Special Interest Group of Operating Systems Hall of Fame in 2020, so 3 years ago. And he's also been made a fellow of the ACM. The ACM is the largest and oldest professional organization of computing professionals. And presently, he's working on a proper systems design, that is, system being hardware and software, around the Ancient computer, which is a hybrid CPU FPGA machine that is really sort of geared for high performance computing applications and designed for systems research. So it's an accessible system. You can actually get your hands on it and get copies of it if you like, as far as I know. But I'm sure Timothy will tell us all the details about it. So can we start the video, please? As I said, Timothy, unfortunately, we couldn't get him here in person, so we have the video, but he will be online for the Q&A afterwards.
Hello, and thank you so much for the invitation to give a John Lyons lecture. I would have really loved to have been there in person to give this talk live and to meet you and chat with you and catch up with some old friends even. It's a shame that the travel didn't work out in the end. Hopefully this will still be a worthwhile talk. This is a talk about operating systems, which seems appropriate for John Lyons. And in particular, it's about what operating systems do and the extent to which modern operating systems actually really do that in reality. So I'm going to make a somewhat surprising argument in this talk. Okay, I'm going to claim that modern so-called operating systems, Windows, Linux, iOS, Android, the like, are not really functioning as operating systems, given what functionality they're supposed to have, right? This was interestingly not the case when Lyons wrote his commentary, but it is today, and operating system design has, in a sense, since that point, failed. And part of the reason that it has failed is that while modern operating systems are still written for hardware that looks really quite similar to that used for the Unix 6 edition that Lyons wrote his commentary on, a real modern computer, like a laptop or a phone or a data center, doesn't remotely resemble this. And this is bad, and it has some far-reaching consequences. But I don't think the situation is completely hopeless. I think it can be fixed, and I'll talk a little bit about that. So what exactly is an operating system? Okay, you can find two different definitions of operating systems out there. This is the first one. It's ontological, and it's not terribly useful. It says that an operating system is a kernel, a set of daemons, runtime libraries. It's kind of vague, but worse than that, it says nothing about what the operating system actually does. In fact, it actively discourages thinking about what an operating system actually does. For that reason, I don't really like using this definition. I don't teach it. I tend not to think about an operating system in this kind of way. I prefer this definition, which is functional. Okay, it says what the operating system actually does or is intended to do. It is that body of software inside a computer that securely multiplexes and abstracts the machine. This captures the problem the operating system is trying to solve. It actually says why the operating system exists in the first place. So I like it. And there's nothing controversial about it. You'll find this definition in textbooks quite a lot. But when we apply it to a modern computer system, we'll see that often it doesn't seem to fit with what we intuitively might think the operating system is. So let's go back to when Lyons wrote his commentary on Unix back in the day. What did a computer look like back then? Well, it looked a bit like this. This is a PDP 1140, which was the machine that version of Unix was written for. Here is Ken Thompson and Dennis Ritchie sitting at the terminal hacking Unix. Roughly speaking, its architecture looked a bit like this. Okay, this is the architecture of the machine described in the commentary. Roughly, it's got a CPU and a memory management unit over here. It's got some memory. Some of that memory was connected to the MMU. Some of it was connected to the Unibus. It's not quite clear which way around it is, but that's not terribly important as a detail. And it's got a bunch of peripherals sitting on a peripheral bus. Okay, in this case, printers, disks, paper tape punch, that kind of thing. So if we compare this to the hardware model that Linux assumes today, and many other operating systems do today, it's remarkable how little has changed. Okay, what we've got here is a set of homogeneous cores, okay, but more than one. That's the big difference. They have caches, they can have cache coherence. There is a single physical address space that everything sits in, including devices. That was actually a nice feature of the PDP-11. It was fairly innovative at the time. Has a bunch of I/O devices, and they're all abstracted by drivers in the operating system. One is a NIC. That's the other big difference, is that the network is there. There's a lot of ways you could design an operating system to run on this kind of hardware, okay? But it turns out that this one seems to have been pretty successful, okay? This is Windows, Unix, Linux, iOS, Android. They all basically look like this. The operating system has daemons, libraries, and a big monolithic kernel. And that kernel is a shared memory multi-threaded program. Okay. The problem is that for the hardware picture that I showed you first, the PDP 1140, okay, that is basically a very accurate description of what the machine was. The second picture I showed you of a modern PC, multi-core PC, is a complete fiction. And we gradually came to the realization that this was a fiction. And we gradually came to the realization of the implications of this fiction over a number of years. And I want to sort of tell you a little bit about how we got there. Okay, so when I first arrived in Zurich in 2007, having spent 4 months in Sydney in the SEL4 group at NICTA, after leaving Intel Research in UC Berkeley, it was an interesting time for me. I was a professor for the first time, and also for the first time, really, I was actually in charge of my own research group. So I got to choose what to do. I was also back on the same side of the Atlantic as some close friends who worked at the time in Microsoft Research, notably Paul Barham, Rebecca Isaacs, Tim Harris, and others, with whom I'd been talking for a long time about what a new operating system would look like for modern hardware. And so it was a great opportunity to try this out. It was also, though, a very interesting time for hardware, okay? So the phrase on everybody's lips at the time was, the free lunch is over, okay? Processor cores had stopped getting faster. And this meant two things. The first thing was we expected there to be a lot of cores in computers in the future, okay? Computers would have to scale to hundreds of cores because that was the only way to make effective use of the transistors that you had on a die. The second thing we expected was the machine to mix processors with different instruction set architectures. And this is purely based on the sort of smart peripherals and smart NICs we were seeing and the way GPUs seem to be evolving towards a lot of the functionality that you saw in CPUs. And so we took this as an excuse to build a new operating system with a very, very different structure to the one that I showed you just now, that could handle hundreds and hundreds of cores and also handle heterogeneous processor architectures. Okay. So we thought we'd build the OS on a single machine as if it was a distributed system. Okay, so nodes, which would be processors, would communicate via exchanging messages, and they would synchronize using distributed algorithms rather than sharing memory with locks, which is what happens in a monolithic kernel. For scalability, we knew that distributed systems could scale to very large sizes in many cases because Google were doing this and they were publishing papers like MapReduce and things like that. And we also thought that shared memory programming was actually going to be harder to get right at scale than distributed programming using message passing. There was also some interesting debate going on at the time about whether hardware cache coherence would actually scale to that kind of size as well, and it wasn't clear at the time. So that was a good argument for making things a distributed system. But for heterogeneity, it was obvious to us that when you needed to have multiple kernels because you couldn't run the same kernel on different processors with different instruction sets. It really didn't make sense. That was not going to work. Okay. And so Barrelfish, the operating system we built, ended up looking a bit like this on a PC. We wrote this on PCs. I want to emphasize that we built Barrelfish on PCs because PCs were what we had available. PCs with as many cores as we could find. Each core, right, had its own very, very small kernel with all of its state represented by partition capabilities. That was an idea that we sort of borrowed and extended from the SEL4 work. Kernels didn't share any data with each other, and indeed they didn't really communicate with each other at all. What they did was that they ran user space server processes, and those communicated, managed the distributed algorithms that synchronized the state across the kernels in a distributed fashion. Now, above this, you could write, shared memory programs for the hardware if you had cache coherence and you wanted to use things that way. But the key thing was the operating system itself didn't need it. Right? The operating system was completely agnostic about cache coherence or indeed shared memory. Okay. Now, when I talk about Barrelfish as a distributed system for an operating system, that needs qualifying a little bit. Okay, so Barrelfish didn't need shared memory, didn't need cache coherence in any way. It was fine with just message passing, had no problem handling the kind of associated asynchrony. It certainly handled heterogeneous architectures. That was fine. We just had a nice build system that built different kernels at the same time for different architectures. Okay, we ran all kinds of weird machines, and it worked just fine. We even handled nodes and cores dynamically coming and going, right? You can actually do that with standard distributed systems techniques, modified a little bit for the fact that the numbers are a bit different inside a single computer. But there's some big assumptions being made in Barrelfish that just don't apply in a truly distributed system, okay? So we don't handle partial failures, for one thing, okay? Barrelfish never handled partial failures. The whole system was designed as a coherent whole, right? It's designed from scratch, and it was just not assembled from existing parts. Many distributed systems today are assembled from existing parts. That's essentially its integration job. And crucially, Barrelfish was a single trust domain. Every kernel and every privilege process on Barrelfish trusted every other kernel and every other privilege process, okay? We didn't trust applications, of course. I mean, it was a real operating system. But every operating system node trusted every other node of the system. And this worked because all the code was designed by us. It was running on a single machine. That's essentially no worse a trust model than Linux had. And it was open to inspection, and so on and so on. So, what did we learn from Barrelfish? Well, first of all, it worked. We could run regular programs on it, including inside Microsoft. Andrew Bauman, later of UNSW, used a system called Drawbridge to actually run Microsoft Office on Barrelfish. You could give PowerPoint presentations just using Barrelfish, no Windows needed. In hindsight, scalability turned out not to be the requirement that we expected. Okay, the end of Dennard scaling happened, and that meant that hundreds of cores on a chip never really came to pass. Okay, indeed, instead the most important requirement was the one that we put second, right, which was heterogeneity. And we began to realize this, that this was actually going to be bigger than the scalability problem. As soon as we started taking Barrelfish off PCs and porting it to other processors, like SoCs, kinds of chips that are used in mobile phones. Okay. Now this is a block diagram of the Texas Instruments OMAP 4460, which is the first SoC that we ported Barrelfish to, many, many years ago. Okay. We bought some Panda boards, and we brought up Barrelfish on the CPU cores, the cores that would normally run Android, on this machine. Okay. And those cores are these two over here. Okay. These two ARM Cortex-A9 processor cores here. So far, so good. So what's the rest of this diagram showing? Okay. It turns out that at the very least, as far as we know, what we do know, at the very least, All of these red circles are other processors on the OMAP 4460, okay? And they are all running other software, okay? They handle power, they handle security, they handle wireless communication, they do the video subsystem, all kinds of really, really critical tasks. What is the operating system for these cores? Well, one thing is certain, it's not Linux. And by the time we'd finished with the Panda board, it wasn't Barrelfish either, okay? It was something else that was completely outside the scope of Linux, okay? In fact, even more dramatically, all the little yellow bars that you can see in this diagram, if you look closely, are actually configurable firewalls. Not only is Linux not the operating system for most of this chip, the chip itself is sandboxing Linux into a corner to limit how much it can poke the rest of the cores in the system that are shown in this sort of figure. Now, this seemed very, very different from the PCs that we had originally written Barrelfish on. But was it really? So that was all many, many years ago, okay? But as you may have realized by now, in the systems group at ETH Zurich, we like doing big, ambitious projects. And so around about 2018, we decided to build our own computer for research purposes, okay? And we did build it. It was called Enzian, and here's a picture of one of them, okay? Now, Enzian took a long time to build and debug, but we're really proud of it. It's still kind of unique in its architecture. I'm not going to go into the justification for why it looks like this, or why we actually justified building it, or what we're really kind of using it for. That's a very interesting talk, but it's not this talk. I will say that Enzian is kind of unique still, and it's pretty damn fast. You can think of it as a sort of heterogeneous two-socket NUMA machine, right? We've got a ton of memory and a ton of network bandwidth attached to both sockets. We've got a 48-core ARMv8 SoC in one socket, runs at 2 gigahertz. It's a pretty beefy processor even today. And on the right, you've got the biggest FPGA that Xilinx made at the time, okay? Crucially, they are connected by the CPU's native cache coherence protocol. And there's so many cool things you can do that I won't have time to talk about once you actually have message level access to a processor's native cache coherence protocol and a lot of memory attached to both the FPGA and the CPU and a lot of network bandwidth coming into both of those kind of things. We've got 14 of these machines working. We use them quite a lot for research, and other people use them externally as well. Drop me an email if you want to find out more about it, or you want to use them in your own research. We want to make them available for other people. But interestingly, none of us had really designed and built a computer before. I was lucky to have a great postdoc, again from UNSW, David Koch, with many of the skills that we needed. It was still, though, even with that, a lot of help and a lot of people involved, it was a ton of work. But boy, oh boy, did we learn a lot about what a modern server looks like. Okay, because aside from being over-engineered for research purposes and for having this humongous FPGA in the second NUMA socket, Enzian does actually share a lot of hardware design features under the hood with your typical conventional server class machine. The big difference with Enzian is that in a product, a server, all of that stuff is hidden away from you. You don't see that if you're a user, or indeed if you're installing an operating system on it like Windows or Linux. We got brought face to face with all of this stuff, and we realized how little we and many, many, many of our colleagues, if not most of our colleagues in computer science, actually understood about what a real server computer looked like. Okay, and we had to find out pretty quickly because we were trying to build one. Okay, so what did Enzian teach us about servers? Okay, what I want to focus on here, it taught us a lot, but what I want to focus on here is what it taught us about something called the board management controller. Okay, so this diagram back here is how electrical power is controlled in Enzian, how it gets from the power supply to every component on the board that needs power, every integrated circuit. Every white box in this diagram over here is a discrete chip called a voltage regulator, okay? And it contains its own processor. It communicates with the rest of the board over a network called I2C, and it needs to be told how to distribute power that it gets as input to all of its outputs that go to the rest of the components on the board. Okay, something needs to coordinate all of this. Okay, something needs to connect all these together and decide how to turn on the power and turn off the power and regulate the power to everything on the board, simply to get to the point where you can turn on the main CPU and start executing the code that you might think of as the operating system. Okay? And this is done in pretty much any server you buy today by another processor that the operating system doesn't see. And that processor is called a board management controller. Okay. So the BMC is a whole computer in its own right. Okay. On Enzian, it's kind of somewhat over-engineered, but nevertheless, it's not that over the top. Okay. And it appears on the board. It's in a different chip. It has to handle power distribution, but also fan control, thermal monitoring, clock distribution, all sorts of remote management over the network, all kinds of basic sundry tasks that keep the machine running. And it does this without any real interaction with the CPU or the operating system running on it. Okay? But it can control pretty much every component on the board, including DRAM, including the CPU, including other kinds of things. And it's connected to the network. It's got its own Ethernet interface for management. Okay? So on Enzian, we had to write all the control software for this, all the firmware for this ourselves. And because that was a lot of work, we started with the default open source approach to doing this. It turns out there is a standard open source way of doing it, which means you run embedded Linux on it, on the little computer that's controlling the rest of the computer. And you run a stack that was originally written at IBM called OpenBMC, which is based around dbus, Python, and a lot of shell scripts. Okay? Now, this might worry you. It worried us, even though, in principle, technically speaking, we're not too worried about security in Enzian. It's a machine that's built purely for research. But we were worried that this was the state of the art. Okay. And that's why we're currently working on replacing all that stack with something we're writing ourselves that we feel better about running. It's based on SEL4, and we hope is to verify the whole thing from the I2C stack, which is partly in hardware, or at least on FPGA, all the way up to the control loops at the top. But the conclusion here, right, the key point for this talk is that servers, including PCs, are every bit as heterogeneous as SoCs, and the operating system is every bit as oblivious to the true nature of the hardware, as you would find in a phone SoC that I was talking about earlier. So I want to introduce a new phrase at this point, because I think we're about to run into a problem with terminology, in particular with sort of operating systems, and here's why, okay? Here's a modern SoC. It's a different one. This is actually an IMX8. We use this for teaching. It also runs Barrelfish, it turns out. It's another example of what we saw with other SoCs like the OMAP, and also with servers and with Enzian. It's basically this. A modern computer is a complete mishmash of different cores, smart devices, all running different software, and all sharing the hardware. They can often read and write each other's memory or registers. They can send each other messages that may or may not be interpreted correctly. And they all have to function correctly for the system to work. Okay. However, a so-called OS like Linux is really only aware of a small number of cores that it actually runs on. In this case, it's got 4 A35 cores sort of up here. Okay. The rest of all these various cores run a motley crew of runtime executives, real-time embedded systems, bigger kernels, other bits of microkernels, operating system, bric-a-brac. Okay. And this is the case in a new and different way for every new SoC or system that comes out on the market. And there are a lot of them. I could just go on forever putting these up. And this is why I claimed at the start of the talk that what we think of as the operating system is not really performing the function of an operating system. If you accept this functional definition of an operating system as that body of software that manages, multiplexes, and abstracts the hardware, it's clear that Linux is not the operating system for this, even if it might be a small component of it. The actual operating system, this is what I'm going to call the de facto operating system for an SoC or a server, is, by definition, the sum total of all of this software. Right? It is de facto because, in the words of Douglas Adams, it has not really been designed, it is congealed. Pretty much every computer in the room where this talk is playing is running a de facto operating system. So is this a problem? Oh, yes, it is. So the de facto OS has no design and no definition of correct behavior. It's therefore not meaningful to talk about the kind of trust guarantees that it might provide, or indeed to reason about the correctness in any way. What this means is it's very difficult to make the system better in a principled way. If you don't know whether any particular measure is really going to improve the guarantees that the system provides you. The de facto OS does have some interesting properties, right? Some components in this system are black boxes, right, which are not open to inspection for legal reasons or intellectual property reasons. Partly due to this, there are multiple trust domains within the OS. This is not the case in a typical operating system, but now in the de facto OS, certainly components don't necessarily trust each other. They have to have mutual distrust. For that kind of reason, it can also suffer partial failures, right? Due to either hardware bugs, firmware bugs, things like that. And these, you remember, are quite like the properties of distributed systems that multi-kernel so far have not handled. Okay, so this takes us outside the regular design envelope, even for research operating systems. And yet, this is the reality. This is what's really out there running on these things. So here's a real-world example of the kind of security problems, for instance, that happen here. Right, Qualcomm modem is running its own black box operating system, which is vulnerable to an over-the-air Wi-Fi compromise. Linux trusts the Qualcomm modem because it thinks it's just a regular device. The Qualcomm modem that's been compromised then asks Linux for access through the SMMU to DMA stuff into an area of memory. Linux says, sure, of course, that's fine. That's what you need to do. Modem DMAs into the kernel, it's all over. Now you can patch this, and they did patch this, but it's not fixing the underlying assumptions that led to the problem, okay? These are cross-SoC attacks. And the security people are very worried about this. You get papers on these kinds of things in security conferences. But they're not necessarily the people who are going to architect an operating system in such a way that is still efficient and correct, but doesn't allow these things, or at least has a very explicit notion of trust, where you can talk about whether or not this is a good thing. The furthest you've got is saying, oh, well, this is just a bug in programming the system MMU. Another example here is power management, general efficiency of these things, right? If you're trying to do fancy stuff in Linux with power management, perhaps making use of application knowledge, you've got a problem. All the real power management functionality and policy on something like the IMX8 is running on a completely different set of cores. These ones down here, which are in the system control unit, okay? Linux is unaware of this, okay? The system control unit is trying to second guess what Linux running on the application cores is trying to do with power, okay? There are a lot of power management papers that you read between the lines, right? They're great papers, but you read between the lines and they're basically fighting what the firmware is doing in response to what it sees the operating system doing. Why, okay? Now, again, in architecture conferences, there's a lot of interesting solutions to power management and that kind of stuff. What they're lacking is a coherent operating system framework to put this into. For them, an operating system is Linux. And the problem they have, as with other hardware people in the past, is Linux doesn't have any way of expressing this, and so they come up with a lot of ad hoc solutions. Okay, again, no real attention to this so far from the operating systems research community. So we've drifted into this situation over about 30 years due to operating systems developers sticking to the PDP-11 model because it's what they like and it doesn't require them to rethink the whole philosophy of an operating system. And anything that doesn't fit into that model, they conveniently punt away into devices off stage. Okay, and the ensuing security problems, well, they're just a matter of putting another hack into the kernel to get the SMMU to fix it or something else. They're not seeing this as a fundamental architectural flaw in the operating system. Instead, the operating system has retreated away from most of the hardware. The operating system has sort of gone off and into this cozy corner where it doesn't need to think about most of the issues in the system. But it's the operating system. It's supposed to do that. And under the functional definition of an operating system, that is no longer an operating system anymore. It is simply a small component of the de facto operating system. Hardware designers, of course, have responded to this by building their own functionality. If the operating system isn't going to do the job, they'll do it themselves. And so there's a whole load of point solutions. And of course, again, no coherent architecture, which means that they work in a particular case. But of all the problems that we've seen, just keep arising. There's other, business-related issues and things, but these are the kind of technical problems. At the end of the day, though, the de facto OS is what really matters. That's the thing that runs the platform. And so if you are working on an improvement to Linux or working on some other microkernel or something else like that, you may be doing something very useful. You may be doing interesting operating systems work, but you shouldn't kid yourself that you are going to improve the operating system for a real computer. You might be, but you're not paying attention to what is the real operating system. The de facto operating system is the real operating system. And perhaps if you had that picture, you might approach the problem differently. Okay, so how can we fix this? How can we get rid of all these security, reliability, and efficiency problems in the de facto OS in a fairly disciplined, rigorous kind of architectural sort of way? You've probably been thinking about a number of approaches by now that might actually solve these problems, or you would have expected would have already solved these problems. So I'm going to tell you why most of them might be useful, but none of them actually work by themselves. So the first thing that tends to come up in conversations about this is IOMMUs, system MMUs. They are not a solution to this problem. In fact, they're as much part of the problem space as they are a part of the solution space. There's a whole stream of IOMMU programming bugs that get reported in Linux, for example, and they don't seem to be slowing up. They just keep coming. And that's because correctly programming an IOMMU is very difficult, right? These things are subtle. The models they use are subtle. There's a lot of context switching, a lot of page tables. To get this right and to know that you've got it right, you actually need a definition of correct behavior for the whole system, which in our case, we have not got due to the presence of the de facto OS. Moreover, they're all really about protecting the cores running Linux from the rest of the system, okay? Or just providing translation between IO devices that want to access memory. They don't really address the issue of what devices in the system can access other devices' memory, which sort of is the basis for coming up with a fairly trustworthy structure in a system, or at least a system where you understand the trust relationships. Okay. There are a few pieces of hardware that actually have some protection that aims to do this. Actually, the IMX8 is one of those. It actually has a unit for doing interconnect protection. But that itself is extremely difficult to program. In fact, it's not actually documented in the manual how to program the thing. Attestation doesn't solve the problem either. Right? Attestation basically guarantees that you're running the right set of vulnerabilities on your system. In a modern computer, there are actually so many different roots of trust, actually, that interact with each other in confusing kind of ways. And so the benefits that attestation might actually give, okay, are kind of diluted, right? It's very, very hard to come up with security guarantees based purely on attestation. Attestation provides insight into what a given component should be, and it gives some insight into what a given component must be trusted to do, but it doesn't solve the problem. Unfortunately, for the SEL4 folks in the audience, verifying your kernel doesn't solve this problem either, right? The proofs that are associated with SEL4 are actually very sensible, and they're very powerful, and it's an incredible achievement, and I mean, it's a great achievement, and we love it, and we use it. However, at this point, they're built on sand, right? Because the hardware model that SEL4 has had to assume in order to actually produce these proofs is still basically a PDP-11. So if we're going to get any real trustworthiness on a real computer out of these efforts, and we damn well should because they're really powerful, okay? These verified properties are incredibly powerful, and we need them, but it means we need to really engage an awful lot more with what the actual hardware on a real machine is actually doing. So you could try to redesign the hardware from scratch if the hardware is too damn complicated. And some people are doing this, but they work in a few very closed environments. Reality is that that's not going to work with, say, phones anytime soon. There are too many cores and smart devices that come from vendors who are the only people who can realistically supply that functionality. There are business reasons why it's never going to be possible to create a thing completely from scratch. And in some cases, there are legal reasons why you can't do this. You can't sort of replace the whole system with something that's designed completely from scratch, even if you had the effort to do that. For the same reason, you can't redo this by writing a new operating system from scratch. Okay. There are too many barriers, aside from the engineering effort, to actually supporting all the hardware that you get supported in a system like Linux with a brand new system, even if you could come up with the right architecture. But the real problem is that the de facto OS is in some ways, you know, it is an operating system, it is a multi-kernel, but it's a very, very different environment, as we saw, to the one that multi-kernels were designed for. And a new multi-kernel by itself is actually just not going to solve this problem. So I said at the beginning of the talk that I was nevertheless optimistic. So why is that? So part of my optimism is due to what was achieved here at UNSW and NICTA before it was shut down, at the intersection of formal methods and operating systems, right? So what can we do? The first thing I think to do is to say goodbye to the PDP-11 and to finally admit that a computer is really a whole set of software contexts spread across heterogeneous cores with a complex web of trust relationships, right? Connected by network and partially shared memory, but not fully shared memory, and hardware components that can partially enforce protection based on what other components decide. And we also have to admit that pretty much every computer is potentially different within this kind of framework. So the problem is going to be, how do we end up with a real operating system for a real modern hardware platform that is built up in part from existing components, because we cannot write everything from scratch, that runs existing applications, because we can't throw away the whole ecosystem, supports existing devices and peripherals, otherwise, where's the hardware that it runs on? And crucially, right, that incorporates proprietary and potentially untrusted devices into the framework in a way that doesn't throw everything away in terms of the trust we can put in the system, okay? So we want something that, at the end of the day, we can still make strong formal statements about the trust, security, and correctness of this kind of operating system. And fundamentally, hardware here, not applications or workloads, is the key challenge, and it's the key thing driving this. Before we go off and write more software, let's step back and figure out formally what we can say about existing systems, both hardware and indeed software. And by existing systems, I mean big, messy legacy systems like Linux. First, we're going to need a very detailed specification of what the hardware actually does, what its semantics are. Once we've got that, we can figure out changes to the software that actually make a difference given what the hardware is telling you to do. And maybe in the long run, we'll have some useful advice for future hardware designers at least. So here's one concrete approach. This is sort of one of the things that we're trying at ETH. It's not the only way, I think, to tackle the problem, but it has the nice benefit that, you know, we can absorb many, many contributions within it. First step is write down the semantics of the hardware, okay? And here's our current attempt to do this. This is actually Rust here, but it just constructs an abstract syntax tree for a nice language called Sockeye 3, which actually describes the hardware, and then we can compile this into a theorem prover or into an SMT solver or other kinds of things like that, okay? This gives us a definition of what the hardware means to the operating system. And specifically, it specifies an extended decoding net. So a decoding net has ingress nodes that is cores or DMA devices, anything that can access memory, and expresses how addresses are remapped through the system, okay, when a load or a store happens, okay? And eventually those things will come out and they'll arrive at either a memory location or a device register, or they'll cause a bus fault. An extended decoding network, meanwhile, is kind of symbolic, right? It allows us to express the range of configurability of translation units, like IOMMUs, for instance, or regular MMUs, or caches, or firewalls, or other kinds of things like that, okay? And we think that we've been able to express pretty much any weird form of hardware protection and translation that we've seen in computers so far, with the possible exception of cherry capabilities, which we are currently thinking about. So from here, you can build a graph of trust relationships between what we call contexts, which are things running software, pieces of hardware running software, or look as if they're running software, like devices. And it's based on who can write to whose memory, okay? So, you know, intuitively, if core A can write to the memory of core B, then core B really has to trust core A to get things right, otherwise it could be all over. More subtly, this has to capture also who can reconfigure translation hardware that protects one core from another, because this translation hardware that does the protection is, of course, itself based on page tables, lookup tables in memory, configuration registers, all that kind of stuff, and access to those can implicitly grant access to other kinds of things. So we are now in the realm of authorization logics, and we hope to pick up a lot of useful stuff from authorization logics to be able to kind of do this. Trust here is a very flexible concept. We could talk about, you know, you trust something because you proved it, you could trust something because you've got good insurance. We're agnostic about what we mean by trust here, like many people. So here's a very simple example here. It just sort of shows how this works, right? Here, you know, the NIC hardware can access an area of memory that happens to contain the text segment for the kernel. This is not an unusual situation, sadly, in computing. So if you trust the kernel context, right? You trust that kernel context to do the right thing. You are implicitly trusting the NIC firmware not to rewrite the kernel for you, okay? So any correctness of your kernel has to rely on either an explicit trust assumption about the NIC firmware or a proof that the NIC firmware is going to be doing the right thing. And that proof itself then relies on other potential hardware-determined preconditions. So at this point, we haven't said anything really about software. We've just talked about sort of hardware contexts. In particular, we haven't said anything about software virtualization, whether that's processes, virtual machines, enclaves, whatever. But it turns out that our notion of a context here and trust does actually nicely generalize vertically. It actually can talk about processes and virtual machines in a nice kind of extended way. It just fits nicely into the model. The key insight is that these things are also contexts and that they're created differently by other contexts, by the software running another context. A hypervisor creates a set of contexts that are virtual machines. Trusting the context of a process or a virtual machine implies trusting the correctness of the kernel or the hypervisor that created and manages it. Okay. With enclaves, things are a little bit different because the trust relationship is different, but it's still expressible in the model. So if this kind of model works, and we think it might, right? We are specifying real hardware in this, and we're building tools, and we see what happens. The tools can do some interesting things. We start with a formal description of the hardware and some formal proofs about the behavior of software components based on a set of assumptions about that hardware. We can then feed into that kind of logical system embodied in a tool, a set of assumptions, what we choose to trust in the system, what we choose to trust is going to happen in the system, and see exactly what kind of guarantees can pop out of it, right? Now, you can do this in various ways. Currently, we think actually this might work quite nicely for SMT. I don't think we necessarily need to go for the full interactive theorem prover here. But in this way, we expect to be able to get out exactly what guarantees a particular system can give based on a set of reasonable trust assumptions. And we can do this with a real existing system. And we're going to do that with a real existing system and a real existing SoC and operating systems, and we expect the answer to come out as not very much for the reasons that we've talked about in the rest of this talk. However, at least it's a start. You can now explore the space, right? You can see how changing your assumptions might change what we find to be trustworthy at the other end. And we can also identify additional software proofs that would qualitatively improve the assumptions that come out of the far end, the guarantees that come out of the far end. But we could also identify hardware changes that would qualitatively improve the situation as well. And that's kind of something that we can't currently do, right? We can do this intuitively, but we've got no real handle on what this means. This gives us a nice formal handle on how to do that. What's really happening here, as you probably realize, is some sort of read-eval print loop for exploring trust and assumptions in a de facto operating system based on what the hardware really does, what its real semantics are, and where the software is distributed through that system. And this is where I feel the true impact of something like SEL4 can come in. We can now say exactly what effect replacing an unverified component in the system with a truly verified microkernel with strong properties actually has on the system. And I think this actually means that there's a new, perhaps potentially a new area of applicability for things like SEL4 here, which I find really kind of exciting. Okay. So, other things pop out of this. Once we've got this kind of thing, we have a very primitive version of this, and we're sort of, we're in it's already kind of, fun to play with. But what you come out with, for instance, with a system like this, is what you actually have to prove about a piece of software to change radically the assumptions in the system is now quite specific. You can actually say, look, this proof has to prove that this piece of firmware will not do X, Y, and Z. That's kind of new, right? Very strong proofs like those of SEL4 can cover a lot of these cases, I think. But if you've got a piece of unverified software and you've got to try and figure out what you can do with it, it may be easier to prove something very limited about that software. And this framework gives you a sense of exactly how limited that proof can be and still be useful. We can now identify steps that genuinely qualitatively improve the trustworthiness of the de facto operating system that already exists. We can also try other things, right? We can also use this as a way to find the best place to look for software vulnerabilities, given what the hardware is doing. We can look for, this piece of firmware here is clearly capable of doing something, or this piece of firmware over here is already very, very heavily sandboxed. And so even if that stuff there has some vulnerabilities in it, we're not going to likely find some really cool exploits. Okay, but over here, maybe it's different. And perhaps we'll be able to end up talking to hardware designers about features that we have found make this result really strong, and features we have found that really get in the way, and tell them to remove those features from future designs. So, to conclude, Unix level 6, as John Lyons' commentary brilliantly showed, was very, very closely tied to the real PDP-11 hardware. Today, in contrast, the existence of a de facto OS is a rather inconvenient truth about modern computer systems. Okay? Doing something about this, though, can't really be done until we can talk about what the correct behavior of a system like this should actually be. If we can capture the hardware, on the other hand, in all its complexity, we can evolve the de facto OS towards something with useful trust properties in a disciplined way, in an informed way. And I actually think that the tools for specifying hardware, modeling trust, relationships, generating OS code and proofs, should be, an absolutely standard part of the operating system toolchain, much as the computer, or the build system currently is today. Right? Otherwise, we're just going to stay in denial about real computers, and that doesn't sound like a good plan. It's going to need completely rethinking OS design, however, and this is an incredible opportunity. And I really think that we have all the tools we need to do this, but we do need to think about computers in a very kind of different way. Okay. So I have so many people that I would need to thank for this talk that I can't possibly fit these on a slide. Okay, but this is, I've been lucky enough to work with some fantastic postdocs, great PhD students over the years, including my current crew, and also some awesome masters and bachelor students at ETH. One of the great things about being at ETH is we have fantastic students. And all the faculty colleagues, both at ETH and elsewhere, you know who you are. I've really, really loved the conversations we've had over the years. These ideas, have come out of conversations, and I hope they continue to do so. With that, I'm done. If you're interested in getting involved in any way with this project, please get in touch. We're also hiring, so feel free to email me about that if you're interested in a faculty position or a student place or something like that. And as I said, I wish I could have been there in person in Sydney. I hope it's been okay, but I'm happy to answer questions as well as I can. Thank you very much.
Okay, so hopefully we have Mothy online. I can see you moving. Can you say something?
I can say something.
Okay, maybe we can turn down the gain a bit. But yes, we did hear you. Awesome. All right. Questions?
Okay, I can no longer hear anything.
Oh, okay. We can hear you. Can you hear me? No? Hello? No? Have you... Do we have... You can't hear me, Mothy? Hello? Still can't hear?
I can hear you now.
Awesome. Okay.
I can also hear myself very loudly in echo.
All right. And you're no longer deafening us either. So okay. So now questions. And Tian.
Hi, Moxie. Tian here. Great talk. I really enjoyed it. I have a question regarding to where potentially this problem come from. So
I'm sorry, you're incredibly quiet. And I also can't see anything except an empty podium. So apologies if, apologies if I'm not sure I recognize people because I can't quite see people. But if you could speak up a little bit, that would be great.
Okay, I'll try. I have a microphone here, so okay.
Oh,
so
right.
my question is related with potentially where the source of the problem come from, right? The source of problem is way behind. We are behind. Like our understanding is behind the current industry practice, but now we have some understanding of unimplementation, like how this board currently implemented, popularly implemented, but how we guarantee that our knowledge, which we use to draw all these dependency understandings are up to date and will be up to date. Yeah, so that's my question.
Well, in the sense of how do we know that what we're looking at is the state of the art? Is that what you're asking?
Yes.
Yeah. I mean, obviously, this has long been a problem between academia and industry in terms of understanding what the kind of state of the art is. I think that industry is not, hugely. There's a great tendency to think, okay, industry just never tells academia anything. All this stuff is super secret. The design of any particular server is is typically secret, but the general principles, I think, they were sort of lying there in plain sight. The only reason I think that it was difficult to understand them is that people in academia didn't build computers anymore. It didn't build computers on that kind of scale anymore. We talk a lot with people in industry. They're generally very open about things. I think part of the sort of reason that the de facto operating system has sort of arisen is that people in industry didn't really think to talk to people in academia about this being a problem. They didn't see it as a problem. If you're in industry and you're building a machine, you need to get something working before your product deadline. And you do that by any means necessary. That's just basic, good business practice. And so, in a sense, there's a kind of, frog in a kettle situation here. And that gradually we've got to this point now where the operating system, the so-called operating system, is really doing very, very little in the machine. And a whole lot of other stuff is sort of filling in for it. But I don't think that's ever been a kind of a secret. It just hasn't really been noticed, if you like. So I don't really necessarily see proprietary technology as a huge sort of problem here. Our conversations with people in ARM or Intel or, AMD, Xilinx, these kind of people, it's always been sort of wonderfully open. And indeed, in places like, in Cavium, or Marvell as it's now known, they told us all sorts of things about the inside of the ThunderX chip, which was extremely helpful to us when we were building Enzyme.
So this is really an instance of what we're fighting within computer science for the last half century, of complexity, of things growing faster than our ability to deal with it. And partially that is actually driven by business models, right? There's companies out there, some very big, whose business model is to make things more complex so their competitors have it harder to repeat. So how can we have any hope in dealing with that?
It's an interesting question. In theory, complexity is our business, right? That's what we are all about as computer scientists, is dealing with complexity. I think it's a little bit more complex in some ways than that. I think some of the complexity is simply that these things are doing a lot of stuff, and they're doing a lot of stuff under sort of constraints, So there's a reason that there's a block on that OMAP diagram that I showed earlier, which is marked face detect. Why on earth add the extra complexity of a whole face detection circuit on your SoC? Well, it turns out it saves a huge amount of power, and it's the kind of thing you often want to do on a phone is to find out the faces so you can take better pictures. So I think there's a lot of that complexity is actually inherent. Another source of the complexity is just people design stuff and then unforeseen things happen and they have to evolve it. So you look at the complexity of PCI Express, for instance. A huge amount of that complexity is just legacy stuff. And it's because they had to keep compatibility with previous kind of things. And that's where academia can come in and say, well, okay, what you really want in PCI Express in an abstract sense is something, and then what you actually get is all the rest of this stuff, and that legacy stuff there is there for business reasons. But we can think about these two things to some extent separately. You think about what it really is trying to do, think about all the stuff that's there in the legacy. And you can never really get rid of the legacy. Maybe that actually as academics we should start thinking about legacy support as a first-class problem. I mean, even with things like CXL, for instance, you see all the PCI Express legacy still there. They can't get rid of that package. And maybe we should be paying more attention to that problem. I think there are companies that do use complexity as a business tool. But I think we're smarter than that. I think we can deal with that kind of complexity in many ways for two reasons. One of which is we have a lot of very good techniques for dealing with complexity. And some of the stuff that I just showed now is, in a sense, is a way to throw computer science at the problem of the complexity of hardware. And the other thing is that there's just a lot more of us than there are of them. Okay? And so a lot of this stuff involves writing down things that, you know, an existing specification may not be there. And there's a lot of people who can do that. And I think there's a sort of, you know, we may end up in a situation where it's actually advantageous to have open specifications of things rather than closed things. You could argue that's a motivation for RISC-V. You could also argue that that's a motivation for ARM, who are publishing a lot of formal specifications of how their designs work and how their architecture works. So I guess I'm somewhat more optimistic there. I agree it's a problem, but it's there are a number of causes of the problem, and I think some of those causes we can fix.
Okay, here's one that's been upvoted on the Slido. Did Unix really have access to all the hardware on the PDP-11, or is this somewhat of a simplification?
Any talk is a simplification, but actually on the PDP-11, I believe for the most part, it did have access to it. I owned a PDP-11, not an 1140. Those are big machines. I had an 1134, the one with a little hex keypad on the front, which is a much smaller one. I've seen inside those things. There were no extra processors inside that thing. Devices were very, very simple. If you look at the source code for 6th edition and you look at Lyons' commentary on it, you can see what it takes, you know, what's happening in the drivers to say, talk to one of the, you know, RL01s or RKO2 disk drives, and there's really not much going on there. I think it was very shortly after the PDP-11 that things began to get more complicated in that kind of space. And of course, you know, I mean, if you look at mainframes before then, you know, look at IBM 360s with channel controllers, they were already kind of big multiprocessors already. And that said, IBM never had a problem with this. IBM would never sort of claim that the only thing that System 360 ran on was, or OS 360 ran on, was the CPUs in your mainframe. No, it was always the case that, yeah, and there are these channel controllers and you download programs to them and there's a scheduler on there and it manages them. So I think it was, in terms of the operating system design community, you know, really getting attached to the Unix model was probably where the kind of problem started, because once machines evolved not to look like a PDP-11, you could imagine that an operating system's design would evolve in that direction, maybe take more from kind of mainframe operating systems or from other kinds of operating systems, or indeed distributed systems, and it didn't. And it may be that the PDP-11 was the last time we did that. I used to say it was the VAX, and I gave a talk at Bell Labs on the occasion of the 50th anniversary of Unix, and a lot of the original Unix guys were sort of there, and I was chatting afterwards, and they said, of course, actually, even with the VAX, there was more going on than VMS or Unix would actually understand. But I think with PDP-11, it's a pretty simple machine, right? Maybe some of the fancier ones had more processors.
Okay, any more questions from here?
I should say that, you know, this was all done when I was 4 years old, so, you know, I'm not speaking with authority on this stuff.
Okay, so like you mentioned earlier that like when you have the software on the chips, that the chips were like sandboxing the OS, right? So they couldn't like meaningfully interact with the chips or like control them, right? Would it be more secure for the operating system to be able to control those chips? Because like if the operating system were to be compromised, wouldn't that effectively just give it control of the entire computer directly? And secondly, if the operating system had to interact with these chips directly, wouldn't that wouldn't that create a requirement for drivers for every piece of hardware to be developed for every conceivable installable OS? And would that be better?
Okay, so those are two very interesting questions, and my answer to both those questions is kind of the same, and it is that those are good points if you believe that the operating system is only the thing running on the CPUs. Okay, and so, you know, yes, if the operating system is Linux, and you interpret my talk as saying, well, okay, obviously Linux should be able to control all this protection stuff and should be able to control the I2C bus and talk to the voltage regulators and all the rest of this kind of stuff, then I think your points stand. But you know, with respect, at that point, you have misunderstood the point of my talk. The point of my talk is that the operating system exists, the de facto operating system exists. It already includes all of the firmware that configures all of those security devices. And, you know, it's not, it is not simply Linux. And so what I think you need in an operating system is not a Linux-like operating system. It is not an operating system where a single monolithic kernel controls everything. That absolutely doesn't work in this scenario. What you need is an operating system with multiple trust domains, where there are certain parts of the system that can do certain things and other parts of the system can do other things, and they do not necessarily trust each other. And so there will be a part of the system, probably at early boot, maybe later on, but only under extremely special circumstances, that actually allows you to control some of those protection units. And those protection units' job is to then isolate other potentially untrusted bits of the software, much as it is today, but with a design behind it, to actually sort of, you know, realize that that's what's happening. The way that these systems are structured today to firewall Linux into a corner, okay, is evidence that what the operating system needs to be is a bunch of different domains that may not trust each other. What I'm saying is we should accept that as the reality and design an operating system around that. And that doesn't involve giving, you know, the operating system any new powers, because the de facto operating system already has all that stuff. That's what it's doing today. It's just not doing it very well, if that makes sense.
Hello, that was a really good talk. Thanks for that. So
thanks.
Right now it's a mess. Like the hardware is really complicated, and there's no common interface. So my question is like, should we aim to keep things that way? In that we should accommodate for individual hardware being very different from each other, or should we find a new interface, like common across hardware, so that we can build actual like reliable stuff on top of this interface? Should we find a new PDP-11 and repeat this whole story?
Yeah, that's an interesting question. I think that the question of what we need to do with the operating system, the way we need to think about operating systems, is kind of orthogonal to the, you know, to some extent to this question of, you know, well, you know, should we try and do something about the hardware? I'm very, very wary, though, of, you know, coming up with a new, you know, overarching abstraction for hardware that makes it all look beautifully simple. Because, you know, as I was saying to Gernot earlier on, you know, there's a reason some of this stuff is very complicated. Some of these are market reasons, but some of these are actually really technical reasons. And there's a reason why it's going to get more complicated. You're going to have a lot more specialized cores because you're running out of transistors, you're running out of energy, and in order to get some kind of efficiency, you're going to have to actually start using a lot of very specialized hardware to do specialized tasks. And that seems to be, you know, currently dictated by physics. And so I think it's going to be hard to avoid that kind of complexity. I think there is an interesting operating systems question though, which is how do we manage that complexity? I think we don't really understand yet how to do that, even with things like GPUs, right? You know, GPUs are sort of, you know, a lot of GPUs are quite similar architecturally inside. I mean, those have wildly different performance. But we're still, the abstractions we have for operating system management of GPUs suck. If I'm talking to a GPU and I fork my process in Unix, you forget it, right? Go off and look on the NVIDIA support forums. There's a load of people saying, I was talking to my GPU and I called fork and everything crashed. It's going, yep. It's because we don't have a good way of talking to GPUs yet. So I think we're going to need to do something about this.
Okay, I think this gets us to the end. We're almost out of time, but there's one question that came up repeatedly. One was about the slides. I assume we get those and can post them. The other was multiple people asking, how can I get involved?
Well, we're hiring. But that aside, for the sockeye effort that we just talked about, that's currently proceeding. There's a sort of part of that is a collaboration we have with some of folks in security in Google who are interested in this kind of problem. Some of the other large companies are interested in it. All our stuff is open source, right? We don't do anything that is closed source at ETH. The whole of Enzian is open source. You can download the Altium files for Enzian if you want to build your own Enzian, if you can find a processor. So everything's open source. In particular, you can look for something on called Open Sockeye, which is actually on our. We're not actually hosting it on GitHub. It's on our Open GitLab repo that we run in the department, but it is publicly available. There's a bunch of early efforts in there to specify bits of SOCs, and particularly the IMX8. We're evolving that, but we're working on that entirely in public. And so if you're interested in getting involved, send me an email, but ultimately that stuff is out there, and hopefully at some point it'll be, in enough of a usable state that we can start taking we can take pull requests right now, but hopefully we'll evolve to the point where it's going to be very easy to write down bits of hardware that people are interested in and add those sort of specs to a library, and then also use the basic sort of Rust infrastructure to start building different analysis tools and things like that. So, in traditional open source fashion, there's an open repo out there, and feel free to email me, and I can put you in touch with the rest of the people on the team. And yeah, I'd really like to sort of see this. I think there's a number of other things that come out of this. Well, one of which is just looking at the specification of what a piece of hardware does has a certain visual impact. If you start saying, well, okay, what do we really need to know about the memory management unit on, say, ARMv8 or RISC-V? It's kind of, wow, it's quite scary how much stuff is going on in there. And I think just simply making it clear how complicated a lot of this stuff is, and possibly unnecessarily so. There are some people who say, for instance, that you should be able to do everything you can currently do with the enormously complicated MMUs with a very simple MMU and the right kind of software. I don't know if that's true, but once we've got specifications for these kind of things, you can start looking at kind of functional equivalents and other kinds of interesting ideas. So yeah, get in touch. All our stuff's out there in open source. We'd love contributions to it, and we'd love to keep a discussion going as to what it is. If you're in academia as well, come up and find me at conferences if I make it to conferences.
All right. Thank you very much. We heard a second really awesome talk today, and thanks specifically Timothy putting this video together over the weekend, literally. And it's just a shame we can't have you here for chatting over drinks and dinner afterwards, and I was really looking forward to having you in the lab. I have my own personal follow-up. I will be in touch. So thanks again, our second speaker, Timothy Roscoe. So this wraps up what I felt was a really great event. I hope you enjoyed it too. And we will have more opportunity to chat over drinks outside. And thanks all for coming. And yeah, we will post the videos, etc. Thank you very much.